Now we'll study different terminologies related to the heat radiation. One of them is the amount of heat radiated per unit area per unit time. Now that is what we call it as emissive power, which is denoted by R. Then the coefficient of emission. Now for a given surface, the ratio of emissive power of that surface to the emissive power of a perfectly black body is what we call it as coefficient of emission. Now for a perfectly black body, this coefficient of emission is equal to 1. And for a perfectly reflector, that means no energy getting absorbed, is having E equal to 0. Now we'll try to understand something related to what we call it as Prevost theory of heat exchange. Now heat energy is radiated at all temperature except absolute zero. Heat energy is radiated as well as absorbed from the surface at all temperature except at absolute zero. The amount of thermal energy emitted per unit time depends upon the nature of the emitting surface, its area and temperature. The hotter body radiates at higher rate than the cooler body. Now let us study Kirchhoff's law of radiation. At the given temperature, the ratio of emissive power to the coefficient of absorption of a body is equal to the emissive power of a perfectly black body at that temperature for all wavelength. Now to study it, we'll construct an experiment. Consider body A to be an ordinary body and B to be a perfectly black body as shown in the figure. Now they are same in shape and size. Consider them to be a spherical body. Now they are kept into a chamber which is insulated from the surrounding so that there is no loss of energy, heat energy taking place to the surrounding. Now let Q be the amount of energy which is incident on both the bodies per unit time. Then A will absorb Q amount, Q by QA is the amount of heat energy which is absorbed by the body, ordinary body A. Whereas perfectly black body will absorb the total energy which is incident onto it, that is Q. Now both body A and body B remains at the same temperature. So whatever they will absorb, they will emit. So amount of heat energy absorbed by body A is equal to the quantity of heat energy emitted by body A, which we can write down as A into Q, which is equal to R. Now for a perfectly black body, this amount of heat energy absorbed is equal to the amount of heat energy which is emitted. So that is Q is equal to RB. So I can get A is equal to R divided by B. But as we know, R upon R, B is nothing but the coefficient of emission. So from the above equation, we can get A, which is equal to E. Now let us try to understand Stephen's-Boltzmann's law. The rate of emission of radiant energy per unit area, or power radiated per unit area of a perfectly black body, is directly proportional to the fourth power of the absolute temperature. So we can write R, which is proportional to T raised to 4, or I can write down as R, which is equal to sigma T raised to 4, where sigma is constant of proportionality. It is also called as Stephen's constant. Now if Q is the amount of heat energy radiated for a time T by a perfectly black body of surface area A at temperature T, then we can write down Q is equal to sigma A T raised to 4 multiplied by T. Now if the body is not perfectly black body, then we need to make a correction by multiplying emissivity E of the given body. So the equation becomes Q, which is equal to E into sigma A T raised to 4 into small t. Now if the surrounding temperature in which the body is kept is suppose T0, then the amount of heat energy radiated will be given by Q, which is equal to E into sigma A T raised to 4 minus T0 raised to 4 multiplied by small t. Here we are taking into account the surrounding temperature also. Now I'll study the spectral distribution of a black body radiation. The rate of emission of per unit area or power per unit area of a surface, obviously a perfectly black body surface, is defined as a function of wavelength. Now see in the diagram on the left part, at a given temperature the energy is not uniformly distributed. Here we are plotting a graph of radiant energy emitted or radiant power to wavelength. At a given temperature, the radiant power emitted initially increases. With increase in the wavelength, it reaches the maximum value, and then with further increase in the wavelength, the radiant power goes on decreasing. The wavelength corresponding to radiation of maximum intensity, we denoted by lambda max, is the characteristics of the temperature of the radiant body. Now the area under this curve represents the total energy emitted per unit time, per unit area by a perfectly black body at all wavelengths. Now the wavelength for which the emissive power of a black body is maximum is inversely proportional to the absolute temperature. This is what is called as Wind's displacement law. Now we can write down lambda max is proportional to 1 upon T, or I can write down with constant of proportionality as B, I can write down lambda max into T, which is equal to P. Is inversely proportional to the absolute temperature. This is what is called as Wind's displacement law. Now we can write down lambda max is proportional to 1 upon T, or I can write down with constant of proportionality as B, I can write down lambda max into T, which is equal to P.